2, 1. Astrophysicist, Dr. Raleigh. Does that get you go just hear the astrophysicist? But I am an because you were a kid, right? You said you were a kid, and so now that you've actually done it, it probably does make you want to say woo.
It really does.
Dr. Valerie Rapson. I'm sorry, let me get that out. Astrophysicist, doctor, which is, you should be stoked
I'm
to
super
call yourself
excited.
a doctor.
You know, it took me 9 years of college, so yeah.
It's woo-worthy.
It was woo-worthy, for sure.
Oh my god. So Valerie's gonna hurt my brain a little bit.
I'm gonna try.
Why are we alive?
Well,
why,
okay.
How does
that
Earth...
one's a little deep, but you know.
But why? Okay, so why is there life on Earth?
Sure, no, I understand.
But nowhere else that we've looked so far.
Yeah. So, you know, when we look around, we only see us, right? So we feel special. We've got plants and animals and humans and microbes on planet Earth. And everywhere else we've looked in the solar system, you know, there's no little green men walking around. We haven't found anything else yet. So we feel like we're very special. And we are right now until we find other aliens out there, if they exist. A lot of scientists, including myself, are very hopeful and think that we probably will someday find some sort of aliens out there. But you know, as of right now, we are special. You know, I can't really tell you exactly why we're here, but scientifically it seems like, you know, this is just the right place for us to be.
So you told me earlier, the whole reason you got into physics and then astronomy and then astrophysics was because you were fantasizing about aliens as a kid.
Oh yeah.
So that is still your goal, right?
Oh, very much so. I mean, basically, the day after I came out of the womb, my father sat me down. We were watching Star Trek. So I think that was just engraved into my brain since I was a baby. And then as we grew older, we watched a lot of sci-fi. And as I said, I delivered newspapers as a kid. And we listened to those late night TV shows where people that were supposedly abducted by aliens called up or just, you know, saw something weird in the sky. And, you know, 99.9% of that is probably complete craziness. But it really intrigued my teenage brain. You know, I didn't want to become a crazy alien hunter or jump into the conspiracy theories, but I wanted to just try and understand more and be practical about it and see how far I could get in if the government would tell me anything, you know, just trying to learn more about it for sure.
Did you watch the X-Files? Or are you a truth is out there person? That was a little bit before you were a teenager.
I think so. I haven't watched too many X-Files. I've been watching, you know, lots of Star Trek, some Star Wars, Doctor Who, a bit of the Twilight Zone, which was way before my time, but, you know, revisiting that has been great, so.
Do a lot of these shows or movies get the physics right?
You know, some of them do, and a lot of them, since they're sci-fi, they're really predicting into the future. And Star Trek has been a great one that, you know, you can read all about this all over the place, of the things that they were writing about in the 60s and 70s that are now true today. You know, they basically had cell phones and pagers and computerized systems that they talk to, and, you know, now we have Alexa and Siri that we talk to. It's really just a modern day version of Star Trek in a sense.
You know what's one of the funniest things I've heard about Star Trek is William Shatner. I forget who he was talking with. It might have one of his shows he had, because he's also, like, besides being that Star Trek guy, that's a real life passion for him, apparently. And he said, I forget who he was talking with, but the person he was talking with said the craziest thing about watching Star Trek, because he could believe all the other stuff, the talking, the warping, and the beaming me up part. He's like, but the part I would not believe is that those doors would just open and slide open.
Right.
And he's like, I had no way of imagining that somebody would walk up to a door and it would just open. I couldn't feasibly think that. And like
that's one of the simplest, easiest things that like every grocery store has that. You know?
Grocery stores have it. And Shatner said it was just a dude standing behind the door and just like pulling it. He's like, oh yeah, the technology did not exist at the time. We couldn't even imagine how it would happen. So we just had this dude whose full-time job was to open the doors for Captain Kirk.
Yeah. Oh my gosh, that's awesome.
So you got to be stoked about exoplanets.
Oh, very much so.
What we got going on?
Yeah. Oh man, so I looked just before I came here, because literally every day the number changes, the number that we've discovered, and we're up to 3,502 official exoplanets out there. And then there's, of course, this huge long list of potential ones that's like almost 5,000 exoplanets long. So we're really on a roll here of discovering them.
And this is looking at how much of the sky have we looked at?
Just very, very small pieces. So most of this data came from the Kepler spacecraft, which is a spacecraft that we put up in 2009. And it was basically, well, it still is. It's trailing Earth in its orbit around the sun. And it spent most of its lifetime so far looking at a tiny, tiny patch of the sky in the constellation Cygnus. So in our summertime sky, you could look for Cygnus. And it's just a really small chunk of it, not much bigger than the full moon on the sky. And it's in there that we've discovered most of these thousands of planets, and that leaves, 98% of the rest of the sky unlooked at so far. So that's just a very small piece. And there's a couple other missions looking in other places, but Kepler really focused on that one spot in the sky because we need to look for a long time to discover these. We're not just going to look for an evening and see thousands of planets. We have to wait for them to cross in front of their star, block out some light, and exactly when that's going to happen, we don't know. So we have to wait patiently and hope that we see it, and that takes years sometimes to see.
Build on my elementary education on this of a planet crosses in front of a star and we see a dip in the light.
Exactly, yeah. So if you've got a star which is self-luminous, right, it's creating its own energy, and if you've got a planet that then crosses in front of it, the planet is just a small rock or gaseous planet, and it basically blocks a tiny fraction of light based on how big the planet is. So a planet like Jupiter is, really only blocking a few % of the sun's light when it crosses in front of it from some outsider's perspective. So that's really what we're watching for is these planets, they cross in front of the star, they make the star appear to dim just a little bit from our perspective on Earth, because we're only looking at the star, we don't actually ever see the planet itself. We just see the star dim, and then based on how much it dims, we can infer how large the planet was that crossed in front of it. So we have to wait, years for this to happen. I mean, planet Earth goes around the sun once a year. So if some alien civilization is watching our solar system, doing the same thing we're doing with Kepler, they have to wait 1 Earth year to see Earth cross in front of the sun and block out the light. And then they got to wait a whole nother year to see it again. So that's basically what we're looking for is these planets that take years and years to go around the sun, or their star, really.
Oh my God.
Yeah, so that's why it takes so long. I mean, and considering that, in the last, Kepler's been up since 2009, so that's, 8 years, and it hasn't been functioning at full capacity for all of them. We're up to 3,000, 3,500, which is pretty good, considering, and there's probably so many more out there that we just haven't been looking long enough to find them.
Oh my God. So is it right? Was it 1995 that we discovered the first exoplanet?
Yes.
That's it. Mm-hmm. So we're like pioneers. We're still in the pioneer state. We don't know what we're doing. We're like Christopher Columbus right now,
Pretty
right?
much, yeah.
Like we have so much work to do.
Exactly. I think 1995, I believe, was the first sun-like star, and somebody can correct me if I'm wrong, but, it's only been really the last, 20 years or so that we've had the technology to do this. And once we realized that other planets were out there, because before 1995, we could have been the lone planetary system in the universe. We honestly didn't know if there was other planets out there. And now that we know, we really push the technology and the telescopes and the cameras so that we could discover new planets, So we've been really working towards that.
Have we found any there's something I heard or read recently about all of these stars that we are looking at and these solar systems that we are kind of mapping out. We haven't found many or any that have, say, like a Jupiter, a gaseous giant. They tend to be in other solar systems. Of course, correct me if I'm wrong, because I'm just talking out of my ass. But what I recall is those gaseous giants tend to be closer in orbit.
Yep.
And our Jupiter is way outside.
Yeah.
And that's what is making us think we're a little bit different. Our solar system is abnormal compared to everything that we're seeing.
Exactly. That is incredibly bizarre. And I mean, if you had asked astronomers to place bets back in the 90s about this, I don't think anybody would have said we're going to find Jupiter-sized planets that orbit stars in days' time. I mean, you can compare that to Mercury. Mercury goes around the sun in 88 days, so it's much closer than the Earth, but 88 days is still a long time. We're talking about a Jupiter-sized planet, 10 times the size of Earth, made of pure gas, orbiting a star in 2 days. So it's ridiculously close, ridiculously hot, and it shouldn't be that way because that's not how we think physics works. Like, we have the terrestrial planets, the rocky planets close to the sun, because the sun has a solar wind. It's blowing material away, which means that a lot of that gaseous atmosphere, if the terrestrial planets had it in the beginning, got blown away by the sun. And our sun, is no different than any other stars in the sky, so we expect those stars to have winds, and they should have blown away the atmospheres as well. So these Jupiter-sized planets that are very close to the star, they're probably not planets that formed there. They must have gotten kicked in or pushed in closer, because all of the physics that we understand tells us that a Jupiter-sized planet will not survive that close to the star for very long. So it doesn't make sense at all. Like,
oh God,
it's crazy. Yeah, like, astronomers, as far as I know, are really still like up in arms of like, how could this happen? Because it's not just one. It's not like we found one bizarre planet and we can say, oh, that's just a statistical oddity, no big deal. Many of these planetary systems have one or more Jupiter-sized planets that are close to these stars. So how the heck they formed, I don't know. And I don't think astronomers know yet either. They're working on trying to figure that out. My
God. Would you say, so I've heard for years that Jupiter, we owe our existence to Jupiter. Mm-hmm. The something Levy with the comets.
Yeah.
Was it 94, 92, something like that?
Early 90s.
Yeah. Like, we saw an example there of having that gaseous giant on the outside of our solar system, and it like sucks in the shit that would blow us up, right?
Yeah,
and kill us.
Yeah, I mean, it acts as kind of like a sweeper. So, Jupiter is much larger. It's at least 10 times as wide as Earth, and it's got a stronger gravitational pull. So a lot of our large asteroids and comets that come through are attracted to Jupiter, or Jupiter will gravitationally interact with other things and basically sweep out a path and clear the path. I mean, that doesn't mean that things don't hit Earth, because they hit Earth all the time, but many of the large objects are kind of pushed away by Jupiter, especially in the very beginning of our solar system. There was a lot more junk flying around, and Jupiter really did kind of push it away in a sense. So yeah, we do owe our existence to Jupiter. I mean, something large could have crashed into us and destroyed planet Earth in the beginning, and we wouldn't have been here. So yeah, I mean, that's another thing to think back about these other Jupiter-sized planets that are close to the star. If those planets don't have a Jupiter further out, can there be Earth-like planets there, or have they been destroyed? We don't know, and we haven't been looking long enough to see if there are Jupiters out at the distance that our Jupiter is from the star. Because Jupiter takes, I think it's 5 years or so to go around the sun, so we've barely been staring at single stars with a telescope like Kepler for 5 years. So we're just now getting to the point where we could even maybe see the first transit of a Jupiter at that distance. So there's a lot of weird questions that still need to be answered in this whole exoplanet field.
Are we just waiting? Are we is this a waiting game?
Yeah, I mean, we're playing the waiting game, but I mean, a lot of work is being actively done. So it's not like we're just going to sit there and wait until we see a Jupiter. There's tons of stuff that we're seeing along the way. So, I mean, at this point, there's 3,500 exoplanets, so that's 3,500 PhD theses that could be written, basically. So, there's a lot of data out there, and lots of telescopes, both in the ground and in space, are studying this. So, but yeah, it's going to take a while. It's probably going to take another 10 or 15 years to really have a good understanding of how these systems formed, and if Earth-like planets with life on them are possible in these systems, purely based on the dynamics of where the planets are, and if there are any terrestrial planets at the right distance from the star to have life on them.
And we're only talking about our galaxy, right?
Oh, yeah. This is stars that are fairly close to us in our own galaxy. I mean, there's billions of galaxies out there with billions or trillions of stars of their own, probably trillions more planets. I mean, we're talking ridiculously huge numbers that I can't even begin to try and really describe.
Oh, my brain just shuts off.
Yeah.
When you say trillion galaxies, trillion planets.
It's like, I know what a trillion is, but I can't really think about it in a way where I really grasp the size of that number,
Is that a product of our evolution? Our brains are just we see just what's in front of us. We can't think of the distance.
I mean, I don't know. And I actually have some friends who have been kind of looking into this of why can't we perceive really large or really small numbers? We tend to be able to perceive things the size around us, We can look at things that are about the size of buildings or human beings and grasp that size, or we can think about how much money we make and we can understand thousands of dollars. But when you think about the government deficit of trillions of dollars, and we think about planets that are hundreds of thousands of light years away, those numbers, regardless of whether we're talking about astronomy or something like money and terrestrial that we really understand, it's just the size of those numbers that our brains can't relate to. So I don't know.
So there's the big end of that, the size and the distance of all these planets and these stars. Here's where my brain also shuts off.
Okay.
What the hell's a quark? And how small is that?
Right. Oh my gosh. So simple terms, a quark is basically the things that make up protons and neutrons that are inside of atoms, and atoms make up molecules, which then make up all of the pieces of our bodies, and then you can grow larger from there. So exact numbers, I don't remember exactly how tiny a quark is, but we're talking beyond the easily perceivable microscopic scales. And there's tons of cool videos online you can watch that basically take a human scale and both go up into outer space and then go down. And the interesting thing, and I don't know if this is just by chance or what's going on, but we kind of live in the middle, right? So we're this middle size where we can perceive things that are, up a certain height to a certain size and then down to the same scale, but shrinking down to a smaller size. And we happen to be kind of in this central range. And I don't know if that's a physical concept that we don't really yet understand why, or if that's just purely by chance and that there are, human being-like creatures living on much larger or smaller scales. Who knows? I don't know if this is the way it has to be everywhere, or if it's just for us, or what's going on.
Tell me what's going on. Are there aliens?
I wish I could tell you.
I told you, I needed to tell me. You said you didn't have any secrets.
Right? I said I need to get into the government and know all the secrets.
Yeah. Is that what you're waiting for? Are you waiting for a call from NASA or something like deep, dark, black ops, like outer space?
Right, I wish. You know what I saw the other day is they actually have a job opening for a planetary protection officer. And it's exactly what it sounds like. It's basically like being a Men in Black.
Oh my God.
It's literally a real job that pays big bucks in the government, where your job is to go around the country, or the world, I suppose, and understand what different space agencies are doing to get ready to protect Earth from aliens. And I was reading the job description.
Holy crap.
It's like a legit thing. And I was reading the job description because I had to know if I could apply for this job. And in the job description, it says, you have to be a good communicator, you have to be able to negotiate, you need a proven track record of negotiating in difficult times. And it basically made me think that they were asking for someone who has success in negotiating with aliens to not blow up planet Earth. That's the kind of person they were looking for.
Do they say the word alien in the job description?
They do not. But they definitely allude to that, that's basically what this job is.
Is that so? It's like Men in Black. You're right. Don't they help work out the democracy of the universe?
Exactly.
Don't kill those people.
Exactly. In the movie there are lots of aliens and they come and go as they please on Earth, and Men in Black's job is basically to keep everybody safe. When the aliens come out of line, they have to go and correct it. But this is really more like protecting planet Earth. So when the aliens, if they ever come for the first time, whoever this person is that gets the job is basically going to be the person standing in front, greeting them and begging them not to blow up planet Earth. It sounds like an awesome job. I'm not going to lie.
This is NASA?
This is just, I think it would be part of NASA in some way, but I think it's just a general government job. I don't know exactly where it falls. It might fall under the military.
Please apply.
Partly.
Please apply for that.
Alien
negotiator.
I feel like I have to, just to say that they actually maybe considered me for this job.
You never know. You might not get the job. Maybe the job doesn't really exist.
Sure.
But they're going to take people. Maybe if you apply, somebody will be watching you for several years and be like, Valerie, we've been watching you.
You have good negotiation skills.
Yes. we think it's time we tell you.
Right. That would be awesome, right? Just take me to Area 51 now. Show me the bodies.
My God. Oh, God.
They did come out a couple years ago and say that, the whole Area 51 thing, Area 51 is real, but of course there's no actual aliens there. It was just a military testing facility, and but they've declassified the maps that show where it is. So it was a real place. Who knows if there was actually aliens there?
My experience with humans in my existence on this earth,
right.
Nobody could keep a secret that long.
No.
Nobody's keeping a secret. If we had aliens, we would know. If we had, there's nobody.
Somebody would have said something by now.
Just try to keep a secret between.
On their deathbed, right? They would have said, "I need to tell you."
Yes, exactly. Try to keep a secret with 2 or 3 people. See how long that lasts. It's not easy.
No,
it's hard.
Really not.
And now we're talking thousands of engineers and science. So it is just, It's fun. It's fun to imagine we have aliens, right? Mm-hmm. But it's also, we're assuming all these aliens are going to be far more technologically advanced than us, right?
Sure.
So I have a hard time believing that we could capture something, or not capture, or whatever you call it, get our hands on an alien that's probably just light years ahead of us. Right?
And in all honesty, if we think about this in a practical sense, there probably aren't too many aliens out there that are super evolved, that have traveled to Earth and are secretly living among us. I mean, I really don't think that's what's out there. If there's stuff out there, it's probably inert plants that are growing on a planet, or it's probably microbes that are very preliminary, that haven't really turned into much yet, like single-celled organisms in an ocean on some moon or planet. That's honestly what we're looking for, is really more not little green men or giant silver spaceships. It's just evidence for microbes or plant life on some other planet, probably outside the solar system. Our solar system doesn't have too many good chances.
Is Titan still in the running, in the mix?
So Titan is a moon of Saturn, and it is to have a chance. So Titan is cool for a bunch of reasons. Titan is orbiting around Saturn, and it's got a big, thick atmosphere with a lot of nitrogen, and studies of the atmosphere tell us that it's very much like Earth's atmosphere was a few billion years ago, when it was just forming. So that's about the time when life was starting to begin on Earth. So if life, was growing on the planet then, Titan is in a similar situation. The atmosphere and the air is about the same. But the temperature is a huge difference. It's very, very cold on Titan. We're talking like negative 200 and something degrees Fahrenheit. And it's so cold that there is liquid methane on the surface. So there are liquid. It's the only other object in the solar system that has flowing liquid oceans and lakes. But it's not water. It's methane. It's a different chemical altogether.
Can we produce liquid methane here on Earth, or can we not get things that cold?
So I believe we can. I don't know too much about the chemistry, but we have some pretty fancy equipment that can bring things down to very cold temperatures, and we can simulate that in a lab. So some testing has been done, to see if any kind of microbes can live in such a condition. And it's possible that, maybe it's not carbon-based life forms. I mean, we're all made of carbon. That's where our structure begins, but it doesn't have to be that way. Biologically, that seems like the most plausible option.
Because that's what we see, right?
That's what we see, and it makes sense. Carbon makes the most bonds. It's one of the most stable atoms that can make 4 bonds. So to have something else made with a base that's not carbon, it's possible, but it seems less likely. It seems more unstable. Like the microbes in the life wouldn't survive as well.
How about silicone? Can it be or is that something? Is silicone-based life forms? Is that something we have to create? Or is there evidence that can happen naturally?
That's kind of option number 2. I don't know that we have any, we don't have any evidence of silicon-based life form, but it's a possibility. I mean, silicon forms bonds just like carbon does. They're just not as stable, and I don't know that we have evidence of the large carbon chains forming the way that, or the large silicon chains forming the way that the carbon chains do. So I don't know, and my biology and chemistry is probably not up to par, but I don't know.
Those are lame studies anyways.
Right?
Physics and astrophysics. Yeah, that's way better.
But yeah, I don't know that it can fare as well when it starts to create these very long chains of molecules that we need to make up our bodies and life as we know it. I don't know that silicon would fare quite as well. It wouldn't survive as well.
Circle back to the composition of a place like Titan.
Yeah.
How do we know for sure that there's nitrogen and whatever else in the atmosphere.
Well, the cool thing about our solar system as compared to these exoplanets, the planets around other stars, is that we can travel to Titan. We can travel to Mars and these other planets in our solar system. So we've sent lots of space probes there. Cassini is now orbiting Saturn. That's taken a ton of pictures and data of Titan. And then the Huygens mission, which was with Cassini, actually landed on the surface of Titan and survived for a short time. So we have sent spacecrafts there, and we have sampled the air. We've taken spectra, which basically breaks up the light into the constituent rainbow and allows us to study what the atmosphere is made of. And we have, pictures of the ground. We have radar imaging of all of the lakes of methane. So we're pretty confident about what Titan is made of. But looking at exoplanets outside the solar system, we can't, it's pretty impossible to travel there, and it probably will be impossible for a long time. So we've got to rely on what the telescopes can tell us. We might learn a little bit about the atmosphere. We can tell the density if it's a rocky or a gas giant planet. But to go much further than that, we're never going to get a picture of an alien waving at us, at least not for a very, very long time.
All right, so telescopes. We have it's the Webb telescope that we're developing now, right?
Yeah, that's the next big one.
And is that just are we gonna decommission Hubble, or are we just gonna
that's a good question. So Hubble is still up there, and knock on wood, Hubble's doing well. We didn't expect it to last quite this long, especially since we stopped sending astronauts up there to fix it. That was one of the big things about Hubble, is that you could send an astronaut up to fix it, update the instruments when things went wrong. But we stopped doing that. I forget how many years ago, but quite a while ago. So the next thing we're going to do is send the James Webb Space Telescope up, and Hubble's going to keep going because Webb and Hubble are very different things. Hubble basically looks at optical light, the kind of light that we can see with our eyes, and even though it's slightly older technology, it's still doing a great job. We're still learning a lot. The James Webb Space Telescope is going to be bigger, but it's primarily in the infrared. So this is the light that we can't see with our eyes. This is like our body heat, right? We as humans emit in the infrared. And that's the kind of light that Webb is going to pick up, which is different from Hubble. So we might study the same objects, but we're looking at completely different types of light that these objects are emitting and learning something different physically with the two telescopes. So they're going to work hand in hand for as long as Hubble is still up there.
And that's coming up in 2018, right?
Yes, so October of 2018.
My friend's husband works at NASA in Maryland.
Oh, nice.
And she sent me a picture of her standing in front of Webb.
That's awesome.
The big gold plate.
Right, the whole mirror structure.
Oh my God.
That's cool.
Oh my God.
I haven't seen it that much put together. I did have a chance to visit Goddard a couple of years ago when they were testing the mirrors and putting them together. And it was neat to see because I got to see some of the actual mirrors, and each one had its own little temperature controlled pod that it lived in. So it looked like a little alien creature because there's these little pods and each one had the mirror in it, and there was all these sensors because you could never get near anything. And it was very neat to see all the engineering that was going into putting it together.
The thing that boggles my mind about that thing is that the mirror is gold, right?
Mm-hmm. It's gold plated. It's not solid.
Okay.
Yeah.
And just the amount of gold you need to plate that surface is so small.
Right.
Gold is crazy.
Mm-hmm.
Why is gold that crazy? I know we're getting into chemistry here, but...
Yeah, I know, but gold is highly reflective, which is a good feature, right? You're building a mirror, so you have to have it be reflective. And it also holds up very well to being bombarded by stuff. Undoubtedly, James Webb is going to be hit by small little rocks and dust in outer space, and gold is nice and strong, and it will hold up well to all of that.
All right. But it's still... gold, I just thought... originally, I
right,
thought...
of all the
it's fancy.
Pick,
They're just making it expensive unnecessarily. And then I learned
no,
more about it. Nothing behaves like gold. You get to plate something with... There's just a little bit...
Mm-hmm.
Just a little bit.
Very thin layer.
And it's the most important part. It's all about mirrors, right?
Yep. They've got to be reflected. And the coolest thing about Webb is that, it's not just one giant mirror. It's 16 different segments. It's pieces that are put together. And each one is on its own little actuator system, which means you can kind of tip and tilt each piece of the mirror. And once we get it up there, we have to then tilt each mirror just the right amount to line it up so they act as one giant mirror focusing the light into one spot. So it's not like Hubble where it's just one big mirror, one chunk, everything is pre-aligned before you go. And yeah, there were some issues with Hubble, but we were able to fix it. This one, we actually have manual controls over all the different pieces, and we're going to have to adjust things via computers from the ground after Webb is up in outer space.
Oh my God.
So, I mean, we're all astronomers, I think, are very nervous about this. I mean, I trust the engineers, but there can be issues. I mean, we trusted everybody when Hubble went up, and of course, Hubble didn't look so great in the beginning. They ground the mirror slightly improperly. So a lot of testing is being done on the ground, much more than they actually tested Hubble, because James Webb is not going to be serviceable. It's too far out there. It's not in a low Earth orbit. It's much, much further away. So
how much further?
It's at what they call the Lagrange 2 point, which is beyond Earth, so away from the sun. I forget how many miles away it is, but it's past the moon. I want to say maybe 4 times the distance to the moon. I could be slightly off there, but so that put it at about 1 million miles. And again, my numbers could be a little off, but
dude, it's far.
It's far away.
Wow.
And it's also at this point called the Lagrange point, which is like a gravitational well. It's a spot where in outer space, the gravity of the Earth, Moon, Sun, and all the planets, if you do all the calculations, it's a spot where something, a space object, can sit, and it won't move very much. It's not going to float away into outer space. It's not going to get closer to Earth. It's this little well. It's like putting something at the bottom of a pool, and at the very bottom, it's at its lowest point. It's just going to sit there unless something else disturbs it. So the reason we're putting it there is so that James Webb, it will follow the Earth around as it orbits around the sun, but it will stay at this distance and it will stay far away so that we can look in the opposite direction, away from Earth and the sun and other objects that are hot in the infrared, and we can focus on everything else in outer space. But long story short, we're putting it out there, and you can't send a human out there because they would get stuck there too. Like, physics works for humans and space telescopes, so it'd be incredibly difficult to get something back from this Lagrange 2 point. And so, we have to get everything right on the ground. There's no way to really go up there and fix it if something is wrong.
Man, hurt my brain a little bit. How do we know this? How do we know the physics that this Lagrange point, Lagrange 2, exists? And how do we know if we stick something there? Do we have other stuff out there right now?
Oh yeah, we have other stuff out there. The main other telescope out there is called Gaia, and this is a European Space Agency telescope, and Gaia's job is to very, very precisely measure the distances to stars. So precisely that it could resolve the width of a human hair, to the nearest star kind of thing. That's kind of the accuracy that we are going for here when we talk about shifting of stars in the sky to figure out how far away they are. So it's incredibly accurate, and it's great. But Gaia's been out there for a couple years, I think since 2013, sounds about right, maybe a little later. But it's been out there for a while. So it's not the first thing to go out there. Other space telescopes have. But we can do all the math. Basically, you could sit down in a physics course and basically take the size of the Earth, the Sun, and the Moon, and Jupiter, which is really the other big planet, and kind of, figure out gravitationally where all of these points are, just based on the size and the amount of gravity that each one of these objects in space has. And there's a bunch of different Lagrange points. There's one between the Earth and the Moon, so where the gravity balances between those two, between the Earth and the Sun, exterior to that. There's a whole bunch of different points that we can place these objects.
Maybe the simplest question I can ask.
No, go ahead.
And also maybe the hardest question I can ask.
All right. Bring it on.
What is gravity?
I'd probably have a Nobel Prize if I could explain it well enough for you. So gravity is basically this force that we feel, right? So we stand on planet Earth and our feet are stuck to the ground. So for a long time, people thought that something inside of planet Earth was basically holding onto our ankles and not letting us fly away. But then Einstein came along and he said, came up with all of his theory of relativity, and we don't have to get into all the crazy details of that, but basically he said that space-time is curved. So a massive object like a planet, a star, a galaxy, or whatever, it's going to curve space-time. And it's a very similar concept to this potential well, this gravitational bottom that we were talking about. If you've got a planet or an Earth, and you place it down on this sheet of space-time, it's going to bend it like a trampoline. And what we feel as gravity is basically us being attracted to the bottom of the trampoline. So that's kind of how we perceive gravity. There are still theories, there are theories out there that say that there's like a graviton, basically a particle that is responsible for creating the force that we feel of as gravity, but we haven't quite gotten to that point yet. Einstein took us many steps forward. We now understand kind of how and why we perceive gravity, but exactly what it is and how it works is still somewhat up in the air. I mean, we can describe it incredibly accurately, but we don't have a complete picture of gravity quite yet. And that's where, quantum mechanics and astronomy basically have to meet. And they haven't met yet. We're talking large-scale astronomical things meshing with teeny tiny graviton microscopic particles and how those two interact on a quantum mechanical, a very small mixed with a very large thing. Because it appears to be a very small object, if it exists, creating incredibly large-scale effects.
Now, is that the theory of everything?
Yeah,
so-called?
Pretty much. I mean, there's a lot more to it than that. But yeah, if we had this theory of everything, it would describe in very broad terms that you could then break down into the details how our universe works and why it works and how gravity has pulled everything together and why we have things that are so large and so small. Why is there such a range of objects?
My God.
Yeah, but we're not quite there yet.
My God.
I mean,
No.
It's going to take some time and a lot of brains, more brains than you've got right here sitting in front of you to figure all of this out.
Now, EMC equals MC squared, yes. Einstein's theory of relativity. Mm-hmm. At this point, we're approaching, 100 years or so since he first proposed it, right? Now, that's been run through the ringer nonstop, right? Mm-hmm. Like, scientists love crapping on other scientists and proving them wrong. Uh-huh. So we've tried to disprove that for about 100 years, right?
Yeah.
So we're really confident that everything holds true.
Well, as far as we can tell, a lot of it is holding true. And we're still kind of working towards figuring it all out. And I wouldn't say that we're attempting to disprove it, but we're still trying to prove all the pieces. And one of the big pieces that we just recently discovered was, of course, gravitational waves. So you probably heard about it. It was, over a year ago now, believe it or not, that...
Let's pretend I didn't.
Okay. Well, gravitational waves were discovered. So they basically found two black holes in outer space that were orbiting around each other. They got so close that they eventually collided. And in this spinning and colliding process, they emitted gravitational waves, basically wiggles in space-time, like dropping a pebble in a pond and watching the waves travel outward. This is what we're seeing, but in our universe. And these were predictions of Einstein's relativity. So it goes beyond E equals mc squared. That's just a small piece of it. But, that was the discovery of gravitational waves, which came out of Einstein's equations, was just one more step forward saying, yeah, Einstein was correct. But, of course, there are things that, the expansion of the universe that we can't quite understand yet. When we talk about dark energy causing everything to fly away and this mysterious dark matter which is interacting gravitationally with stuff in our galaxy, bits and pieces of that could be in relativity, could be an extension of that. Relativity is a wonderful thing and huge step forwards, but it's not complete. And even Einstein knew that it wasn't complete. So we have some steps forward to go. And as far as we can tell, pretty much everything that Einstein predicted through relativity has turned out to be true. And it's taken us over 100 years now to actually prove it for real, other than just on a piece of paper mathematically.
Now we have these telescopes. Mm-hmm. Now we have thousands or millions of people studying this crap. We have a lot of government money behind it, right? Yeah. God,
well,
we're such dumb monkeys. We're still monkeys. Yeah. We're still dumb monkeys just figuring this out.
Right.
Like I try to remind myself that of all the time. Like, oh, I know this. I know nothing. None of us know. We don't know anything. Right. We don't know what direction this is heading in because we just started.
Exactly.
But this is the question. There's not a person on Earth who hasn't thought, what the hell? What's going on?
Oh, yeah.
Why are we here?
Oh yeah.
And we have no clue still. Mm-hmm. Like we have. How far along do you think we are? Like, best case scenario, is it 100 years? Is it 200 years?
I mean, I don't know because I don't know where the end is, right? We know of these things like dark matter and dark energy, which are two very different things, are huge mysteries in astronomy, right? And dark matter and dark energy account for 96% of the universe. If we're looking at like mass of the universe, that's how much of the universe we don't understand. We understand 4% of the universe. Right?
And then you're talking like 4% is actually made of atoms and matter.
Exactly. So all of the stuff we can easily perceive, the stuff in our three-dimensional universe that we can tangibly touch and see and observe, that emits light, all of that stuff, that's only 4% of the universe. So 96% is still a mystery. Now, it could turn out to be something very simple, like dark matter or dark energy could be one simple, easy thing that we haven't discovered yet. Or it could be this incredibly complicated other thing that's going to take hundreds of years more to figure out. Like, I don't know. We're not looking for one thing. We're looking for an entire theory to explain this. And it could happen tomorrow, or it could happen hundreds of years from now. I really can't even begin to say where it is. And then, of course, it's going to open up new questions, right? Like, are we ever done asking questions?
It doesn't feel like it.
I don't think so.
It just seems the past 5 years of me just being superficially paying attention. Mm-hmm. It has really been the last year or so that I'm like, all right,
sure,
this is becoming a passion.
Right.
But even just the last 5 years, I'm like, they discovered what? Mm-hmm. They did what now?
Right.
Huh? Who?
Right.
Where? Dark matter? Dark energy? We don't know what they are though. Black holes? Wormholes?
Right.
Yeah, and the universe expanding is you mentioned that.
Yeah.
What is that about? Like, it's moving faster than light, right?
Right. Yeah. So yeah, and that's a very complicated thing too. So basically, if we look at galaxies that are very, very far away, when we look at them, we can look at their spectra. We can study what they're made of. We can break the light up into the colors, and we can look for the fact that they're moving, essentially. So their spectral lines, the lines that tell us what their composition is, are shifted into the red. They are shifted to longer wavelengths, which tells us that they're moving away. And no matter which direction in outer space we look, or 90% of the galaxies that we look at, they're all moving away. So we know that the universe is expanding. And then more recent studies have shown us that not only are things moving away, the further away we look, the more these lines are shifted. The faster they appear to be moving away from us. So something, and that's where dark energy comes in, something appears to be this accelerating force in the universe that is pushing things away faster and faster. And why and how and what, and you can ask me those questions and I can't answer them because there's no...
But it's happening to us. It's right
happening.
now, you and I are sitting on Earth in a room in Troy, New York, and we're moving, getting pushed by this dark energy, right?
Sure.
Are pushed or pulled? Do we
so, and we should clarify a little bit. It's not like the space between you and I is expanding. It's the space between galaxies. So gravity works on what I'll call small scales, and a small scale in astronomy being like solar system and galaxy size. So the Milky Way itself is not stretching out. If I look at one star versus another, they're not moving away from us. Okay. It's only the galaxies. It's the space between the galaxies. But yes, if you go to Andromeda, the next door neighbor galaxy, and you look at us, okay, that was a bad example because we're colliding with each other.
Yeah.
But okay, let's pick another galaxy that is moving away from us. And, you looked at us, we would appear to be moving away from that galaxy as well. So we're not in the middle. Every galaxy is moving away from every other galaxy. So there is this energy that's affecting the galaxy as a whole in some way, causing space-time to stretch out and everything to move apart. And again, why this is happening, we don't know. If it will happen for eternity, we don't know. There's many different options for what happens to our universe. We could expand forever. We could continue to expand, but eventually stop until we get to a constant rate. Something could happen and we could recollapse on ourselves. We might look at this in another billion years and the galaxies might all be moving towards us. We might be collapsing again. So we're kind of at this turning point where we can make an observation now, but predicting what's going to happen in the future is still something difficult. We have nothing that's going to tell us what's going to happen in the future. And right now, all we can say is that things are expanding and they appear to be continuing to expand.
Which is terrifying.
It's terrifying, right?
But it's fascinating. It's so profound. that your head wants to explode.
It is. And if things continue the way we're going, like, the sad part is that eventually, and we're talking like billions and billions of years in the future, but other galaxies and objects in space are going to expand away from us to the point where we're not going to be able to see them anymore. Right? So, like, we will, if humans are still around, then, you know, we're going to think that we're alone because we won't be able to see anything. Things will be moving faster than the speed of light, beyond our limit of seeing, and stuff has already passed that limit. So there's stuff that we'll never be able to see because of this limit, and then we'll just cool off and essentially freeze to death and die alone. Like, it's a very sad ending to the universe.
Oh my God. How do we... So is this expansion of the universe... And you just made me feel really sad, so I'm going to try...
I'm sorry.
No, it's totally true.
Ask me a good question.
No. So is this That hurts. That one hurt a little bit.
Sorry.
I don't want to be alone.
No,
or maybe I do. Which is more fascinating to you? The thought that we might be alone. That we're it.
Right.
Or the concept that there's a lot of similar beings, intelligent life out there.
You know, it seems so implausible to me personally that we could be alone, right? Like, I feel like we grew here, we evolved here, and there are so many other planets and places in this universe that it seems statistically impossible that we are the only creatures. Even if it's 100% chance that we arrived on this planet and evolved here, it seems like there are such large numbers. There are so many other planets and planetary systems that there has to be at least one or two or three others out there, if not millions of others out there. So I really feel like we're not alone, and I think it'll fascinate me either way. But I feel like we can't be alone. There's just...
It'd be so sad.
It would be terribly sad.
Was it Carl Sagan or someone that said something like that? If it were just us, it'd be a terrible waste of space.
Yeah, exactly.
Was that Sagan?
It might have been.
It's brilliant enough. Yeah, it probably is. It probably was Sagan.
Yeah. It just... There's so much out there. And then it lets assume that we are alone. Then why is everything else out there? Like, what's the point? Why not put us on this planet? Why not just put a celestial sphere out there? Like, what the ancients thought was, when you looked in the sky, there was essentially a sphere, like a glass dome that contained all the stars. It gave us something pretty to look at. It was fun. It was entertaining, kind of like we're inside of a cage, basically. Mm-hmm. You know, and it's like, if we were the only ones out there and there's some, you know, being that put us here, whatever the case may be, why not just have that be it? Why put in all this effort to make everything else, all those other stars and planets and galaxies, if there isn't a reason for it? If other life isn't out there to also enjoy it? And that's just a personal opinion, but I don't know.
Please, I love personal opinions.
It does seem like just a huge waste of space and a waste of energy, you know?
Is this a simulation? Is it possible
right?
this is just
a simulation? We live in the Matrix?
Yeah,
you know,
is this the
Matrix? Unplug my head real quick here. You know, who knows? I mean, there's been some work about, like, us living in holograms, and basically what we see is not really real, and, you know...
We are an alien TV show.
Basically,
They're
you know...
just like, all right, give the monkeys big brains.
For all we know,
and
you know,
watch.
it's like, we could be an experiment. You know, imagine that there are some aliens out there way more advanced than us. They took the basics of life, they put it on some asteroid, flung it towards Earth, and watched us grow. You know, we could just be a science experiment for some way more advanced species.
But we wouldn't be alone, which would
we wouldn't be
awesome
alone, which would be
if
awesome.
we weren't alone.
Which would be awesome.
But at one point do they come and say, like...
right?
They're,
like they're pranking us, right?
Yeah,
like on those TV shows where they finally come out and say, it was just a joke.
Yeah. Like, our concept of time is so narrow and short, right? Like, 100 years is a max lifetime, right? Mm-hmm. And so it goes so quick. What if these aliens that are here put as an experiment, like, what if they live to, like, 20,000 years old?
Yeah.
Like, they're just gonna be like, sit back and watch.
Exactly.
And you and I, we're not gonna know.
We don't live forever. You know, it's like, you look around outside, you look at things like fruit flies that live, I don't know what, a day or something. You know, there's lots of creatures on Earth whose lifespan is hours to days. And that we're basically living those hours to days of the universe. We have such short lifespans compared to the 13.8 billion years that have gone by. And the thing that blows my mind too about time is that, you know, we were born tens of years ago, and 13.8 billion years went by before you and I and everybody listening to this show was in existence, right? And then once we die, billions and billions of years will probably go by again. And it's like, we just lived this tiny instant. Like,
we're just a continuation
it seems like
of whatever this is. Mm-hmm. Our little existence is so short, and we're just a continuation.
Yep.
It's connecting with nature like this, really, the past couple of years for me, that I'm trying to tell friends and family, like, you got to connect with nature and realize that we are just a continuation.
Exactly.
This is not going to last. So stop taking it so seriously, but take it seriously and try to do the most as you can. As a human, that's really what's been drawing me to studying the stars and talking with people like you.
Yeah.
Because I'm like, I just want to be a better person, because this is going to be over really quick.
Yeah, exactly.
Super quick.
Exactly. And it's like, that's one of the reasons why I got into astronomy and I didn't get, a normal job. It's like, life's too short. This is fun for me. I love teaching people about astronomy. Kids, adults, doesn't matter. It doesn't matter if we're talking about what's your favorite planet or what the heck relativity is. It doesn't matter. It's just exciting for me, and that's what I want to spend my life doing, is talking about all this stuff. And I can't go into the extreme detail that those professors that have been studying it for years can, but I sure can tell you the basics and get you thinking and get you excited about this, because the more people that are excited, the more breakthroughs we're going to have. Because you don't have to be a PhD professor to understand the basics and come up with some brand new ideas. Maybe that's what we need, is not these people that have been studying it for 50 years, but somebody brand new in the field that's got a brand new idea to kick us in the right direction.
It seems once you open up this world to people, it changes their lives. It seems like we're all hardwired to look up at the stars, assuming you can live someplace where you can see the stars anymore, which... what was it, 60 or 70% or 80%? I saw a huge number of people that live in areas where they can't see stars throughout the world.
Yeah, the biggest one is that they can't see the Milky Way galaxy.
Which I just saw a few days ago in Maine. Oh, Maine is so
and it's
dope.
Gorgeous, right?
Oh my God. Here we were signing into it. I went camping with my girlfriend in Maine. We're checking in at the campground, and I asked the girl checking us in, I said, hey, where around here is a great place to stargaze? I want to see the Milky Way. And she told me Cadillac Mountain, which is the first place. Most people know that is the first place in America, in the United States, where the sun hits the continent. So so it's Cadillac Mountain in Maine. And she said she said, I was never a nature person. This is like a 22-year-old girl.
Sure.
And she says, I was never a nature person. I never cared. But I had friends who kept telling me, you got to come out here and see this. You got to come up to this mountain. You got to see the Milky Way. You got to see the sunrise. It'll change your life. Yeah. She's like, what? She said she was blown it off.
Right.
She's like, then she finally succumbed and gave in and went. And the look on her face, she says, it changed my life.
It does.
Like, what? Like, she started getting emotional about it. And I felt it. I was like, that's it. Like, we need more of that. We need to see that.
It's like, we don't think about it because the night sky isn't involved in our everyday lives, but the more we lose it, the more light pollution we put out there, the less we are getting in touch with nature. And if you've never seen the moon or a planet through a telescope, like, you got to do it. Or if you've never seen a total solar eclipse or the sunrise on a mountain, like, it's just spectacular. And it may not change your life completely, but it at least will inspire you to really think about things and understand and connect with each other. It's such a simple thing. Of all the sciences, astronomy is the one where all you got to do is step outside and look up. You don't need any fancy equipment. You don't need to come to a lab. You don't need to do anything. You just need to look up outside.
Just wake up.
Just wake up.
Set the alarm at 2 in the morning, 3 in the morning.
At night, and go. You know? And, we all have phones now. Download one of those cool apps where you can hold it up
Sky
and
map.
tell you, exactly what's in the sky. You don't even have to know anything. You just go outside and look up.
And go, what?
Yeah, exactly.
You said the key word that I think is very important, connection.
Yeah.
And that's, I think, because we feel... That's why I want there to be aliens. I want to feel connected to someone else out there. Because we have a hard enough time connecting to each other on Earth, right?
Seriously.
Right? Like, people, so much of us just go around. We're not connected.
Exactly.
When I look up and see the Milky Way, and I see shooting stars, and I see the Pleiades, which are my favorite. I love the Pleiades. Am I even saying that right? Pleiades?
Yeah.
Though I just feel connected to everything out there, and then it makes me feel more connected to people.
Sure.
And I'm like, guys, we got to figure this out. We got to stop killing each other. We really got to figure this out. Like we're all connected. We're some weird organism like that. So when I take someone else, because this has happened several times the last few months. Brought my telescope. We go to a friend's house. Say, we're going to look at Jupiter tonight. What? We're going to do what?
Yeah,
trust
right?
me. And then I was like, just trust me. And they look in there and they're like, what? Like, you've seen the orange and the white stripes and just the, how, what?
Exactly.
And then you start to feel just connected.
Right.
And you see Milky Way and you're like, oh my God. And then I start to think of civilizations that came before us. Like, what the hell were the pyramids about? What is Stonehenge about?
Right.
What is all of these?
All about connecting with the sky.
Yeah, they're all about the sky. Like, those were sky worshippers.
Yeah.
I don't know what we worship today as a culture. Say history looks back on us in 2,000 years.
Right.
They're going to be like, what were those people doing? But we look back at these people, and that was the most important thing to them.
Sure,
that was the most significant thing they had going on.
Yeah.
And I'm like, we've definitely lost that. Like, we took a hard right turn off of that.
Right. We're watching too much TV now. We need to be outside a little bit more.
Yeah, it's about being outside. That's exactly it. But I like to think our parents' generation, maybe mine a little bit more than yours, kind of screw things up. Like that, people prior to them, they're like great-great-grandparents, they didn't have the light pollution. They lived, they were farmers. They were agrarian.
They could appreciate it.
Yes, they were agriculture. They had to see the stars every night. And then I think our parents' generation just kind of was like, meh. No, we don't need farmers anymore. Nobody farms. Right. And nobody's outside anymore. We've lost that connection with nature.
Yeah. And I think a lot of it turned like after the space race was done too, because people may not have been looking at the stars, but they were really excited about the moon and astronomy during the 70s when we were sending humans to the moon. And then I think that generation really thought that we would continue. I think a lot of people would. And then it just kind of came to a halt for a lot of reasons. But we've lost touch, and there's a lot of astronomy still going on, a lot of great stuff that NASA's doing, but I get questions all the time like, is NASA dead? You know, we're not sending the shuttles anymore, so what are we doing? We're not learning anything about space. We don't care about astronomy anymore. And so it's not just looking up at the night sky, but just understanding that astronomy in general is still happening. There are huge breakthroughs that are going on, and
Elon Musk gotta save us. That dude's gotta save us.
I mean,
come on, Elon, find the aliens.
I just want to jump on one of those space planes and go for a ride. Like, get me in zero gravity. That's what I really want. Like, I don't need to go to the space shuttle. I don't want to be an astronaut because I'm a little bit afraid of like floating away like they do in the movies. Never coming back. But I would go on a space plane and experience zero gravity for a little bit.
I have no desire to jump out of an airplane. Like skydive, that's just not, I don't think I would like that. And especially if I have to be strapped to a person, I don't care for that. But I'd be the first in line. I'd be right behind you.
Right.
Take me to zero G. I want to flew.
Yeah.
So you also said, this, I love hearing this answer because it's just so profound. You said we're 13.8 billion years old, this universe. How do we know that?
That's a great question. So we can look back, we can see how far, we can look at galaxies and we can tell how far away they are just by looking at them, by looking at that Doppler shift, how fast they're moving away. We can do all of that mathematics. We can also look at this thing called the cosmic microwave background, which is the light that was released after the Big Bang happened, about 300,000 years after the Big Bang. Based on what color that light is, it's in the radio wavelength range of the spectrum, we can do all of these calculations of, okay, if the light was emitted at this point, then it should be exactly this color at exactly this wavelength if we are 13.8 billion years old, or whatever number you choose. So it's taking our observations, what we see within the universe, and comparing it with all of our mathematics and computer models to see which one matches the best. And based on those observations of the distant galaxies, the cosmic microwave background, that is how we determine that we are almost 14 billion years old. And we still cannot look back to the very beginning, and that's where gravitational waves is going to come in. Pretty soon we'll have instruments that can actually study gravitational waves from like the very moment of creation. So that'll be really, really cool, because that'll really help prove, if the Big Bang actually happened as we understand it, why are we still, growing in size? Why haven't we stopped growing? And all of those questions can be answered.
Is that the expanding universe and galaxies running away from each other? Is that more evidence of the Big Bang? That
very
there's
much
expansion?
So. Yeah, so basically with the Big Bang, right, bang is not the best word because we think of like this explosion.
Oh, this is marketing.
Yeah,
though.
yeah.
They have to market.
Right,
crap.
they have to do something.
Yes,
so,
like marketing is a problem that science has. It's getting better.
Yeah.
But Big Bang is a great catchphrase.
Yeah, exactly.
Put it on a hat.
Yep. So the universe grew, and it hit this point called inflation, which caused the universe to grow incredibly fast in a very, very short period of time. And then after that, the universe was always expanding. It was always growing. And then all of a sudden, it started to accelerate. And exactly what's causing that acceleration, that's where the dark energy and the questions come in. But I forget, what was your original question? I started thinking again.
Is the expansion of the universe and galaxies running away, is that further confirmation
yes.
of the Big Bang?
Definitely. So as we said, we think about the Big Bang as this expansion point. So the fact that things are still moving away suggests that, if you run the clock backwards, things are going to now move towards you. And if the clock continues to run backwards, at some point you're going to reach a spot where everything's all in one clump, and it had to have expanded from there. So if we had looked at the universe and everything was just sitting still, then maybe we could say that the universe was just there. We wouldn't have any way of explaining how it started because we don't see any motion. We don't see anything that suggests that there was anything in the very beginning. We could have been here for eternity for all we knew. But the fact that there was motion and things are changing suggests that there was a beginning somewhere. Did I blow your mind like how many times now? I just gotta shake here.
I gotta shake my brain out because it wants to shut down, and I don't want to let it shut down. So the James Webb Telescope, is that going to look further back to maybe the beginning of time?
Yeah, so we can only go back so far. The trouble is that all of our telescopes, they look at light. They look at different kinds of light. So the light we can see with our eyes, infrared light, microwave radio, or, X-rays, UV, they're all part of our electromagnetic spectrum, all of the different types of light in the universe. But light has a limit. And if everything we know about the Big Bang is true, then this point where the cosmic microwave background, 300,000 years after the beginning, that is where light, photons, light particles were first released into outer space. So with a regular telescope, no matter how big or powerful we make it, we cannot look back further than 300,000 years after the Big Bang because there was no photons, there was no light to perceive. It was basically blocked. You could think of it as like a wall that doesn't let any light through until after that point. So we need to come up with other techniques to look earlier than that. We need to look at gravitational waves that are not photons, that are not light, because they existed early on and they could travel through the universe before light could be released into the universe. So that's our only goal, to learn more about it.
Okay.
Right now, the CMB is our limit. And James Webb isn't going to help us with that. It's going to help us with super distant galaxies. Like, we'll be able to see galaxies that existed 12 billion years ago. So we're looking back in time more in that sense. We're getting better pictures of distant galaxies, but we're not going to look any closer to the Big Bang than we have already. Not with James Webb.
Okay, so you hit on a good point. If the Big Bang is a terrible name because you're saying there was no bang, because bang implies that there was an explosion, there's light.
Explosion. It's just.
But you're saying we didn't have anything for 300,000 years. That light.
I mean, we had stuff, but we did not have light. So light had to be released. So it was basically a cosmic soup where nothing had really congealed enough to allow light to escape. Photons were there, but they were constantly being absorbed and re-emitted by the material that was in the universe. And it wasn't until this point where atoms could form that light could be released into the universe, and it was not being constantly absorbed and re-emitted. So I don't know, maybe that's not the best way to explain it, but...
No, I'm sure you nailed it. I'm sure it's my brain that needs to catch up.
It's a really hard thing to explain, especially without some pictures.
Yeah.
I wish I could just draw here for you.
Oh, I should have let you draw. You could draw on that.
No, it's okay.
No. I'm going to take your word.
Yeah, just trust me that,
it's a soup. It was a soup.
Light was there, and there was a soup, and it wasn't really a massive explosion. There was some sort of turbulent thing that created the universe. How much of an explosion it was is, up for debate, but something did trigger our universe to expand and grow and cool off. It's this infinitely hot, infinitely dense and small point, and then something triggered it to be unstable, And now all of a sudden the universe is growing and cooling off and slowly forming into what we see today.
So it just makes no sense that to be alive and to be able to talking about
Right.
this,
Yeah, it's
because
just-
something that you can't, you're saying everything.
Yeah.
Everything was something smaller than we can measure. It was all condensed.
Yeah.
Is that now we're dealing now a black hole? Is that's also kind of just a really super highly dense?
Yeah. I mean, we shouldn't think about the beginning of the universe as a black hole because it's a bit different, but a black hole, as Einstein would explain it, is basically an infinitely curved region of space-time. So it's like looking down a well that is incredibly deep. And so we're kind of embedding ourselves into space-time. You're not really going anywhere. It's not a real three-dimensional structure. It's more complicated than that. So things can fall into black holes, and basically any physical object that falls in just instantly gets converted into energy. That's where your E equals mc squared comes in. So any mass that goes in gets converted to energy and density for this black hole. So
Now converted, do you mean destroyed?
basically, yeah. So if you jumped into a black hole, or if I jumped in, our entire bodies would get converted to energy, and the black hole would then gain more energy, more mass, essentially, and grow larger. So it'd have more gravitational pull.
So it just continues to suck everything around it.
Yeah, sort of. So I always teach, especially when I'm doing this with kids, I tell them that black holes don't suck, because we often think about them like vacuums, right? We imagine like you got the hose of the vacuum that's just sitting there and sucking things up in outer space. But it's really more that objects, while they are gravitationally attracted to the black hole, they have to get close enough naturally to fall in. Like the black hole doesn't have continuous sucking power where it's just going to encroach further and further out until it consumes a whole galaxy. A black hole has a definite size and a limit to how far out it can attract things to fall in. So there's a black hole at the center of our galaxy that is consuming material, but it's not ever going to consume Earth because Earth is plenty far away. It's going to orbit around forever. It's not like the vacuum power is ever going to go strong enough to start sucking up the Earth. It doesn't work that way.
Okay.
So you've got to get close enough to fall in, and then once you fall in, you just get converted to energy and you disappear into the vacuum of outer space. Like you just don't exist anymore.
So we're never going to see inside a black hole.
No, not with light, at least, because black holes, their gravity is so strong that a light particle, a photon, cannot travel fast enough to ever escape. Now, that's kind of where, again, gravitational waves start to come in, because when we saw gravitational waves from those black holes that were spiraling in, we didn't necessarily see into the black hole, but we are looking at the black hole in a different way. Gravitational waves, they travel at the speed of light, so they're coming from the outside of the black hole, but they're allowing us to see and learn properties of the black hole that light can't allow us to see. Does that kind of make sense?
Maybe to you.
Maybe.
We
can't actually see these things,
yes,
but we can learn more about them using a different technique.
Okay, you said earlier two black holes colliding.
Yep.
So they are moving? They're just not sucking things in?
Yeah, so all black holes, most black holes are rotating, they're spinning, they have an electric charge, they have
they
mass.
spin?
They do. So yeah.
Okay.
They actually, most of them spin and rotate. So these two individual black holes, they were spinning on their own, and they just happened to get close enough, just naturally in outer space. They found each other, they were spinning themselves, they were also orbiting around each other, and they eventually spiraled in and collided. Because the gravitational waves, they carry away energy, so they can in-spiral a bit more and eventually collide.
Okay, so we've discovered the gravitational waves, but we don't understand them really, right? We don't know what gravity really...
Yeah, so we understand them in a sense that Einstein's relativity explains that rotating objects with mass should create gravitational waves. So we understand kind of the how and why they're created, why they happen, but exactly what gravity is and how space-time wiggles and all of that is still, somewhat of an open question.
Right.
So the gravity part is still strange, but the rest of it, we understand why, because that was a prediction of his theory that this thing would exist, and it just took us 100 years to build an instrument to find it.
All right. I'm going to bring it back home to Earth now.
Yeah, we kept going in all sorts
I'm going to go back to Earth
because
my brain bringing it back in. We got the eclipse coming up in a few weeks, the Great American Eclipse. So that's going to be something we see here. That's awesome.
Yeah.
Now, something I've only recently learned about was Betelgeuse. Do you know Betelgeuse? Mm-hmm. And we're saying that's the best bet of a star going supernova.
Sure.
Is that still true?
Yeah.
Is there a chance we're going to see a supernova star?
There's always a chance that we're going to see a supernova star. So, first of all, supernovas go off all the time in other galaxies, and astronomers do see them all the time. They usually need to have a telescope to look at them, but we can see them. Betelgeuse is, of course, the star in the shoulder of Orion, and that is a red supergiant. It's a star that's reached the end of its life, and it's getting ready to explode as a supernova. And the cool thing about Betelgeuse, as far as we can tell, is that it's like right on the brink of actually exploding. And of all the stars that we can easily see in the sky from Earth, that's the one that seems to be closest to its explosion point. So if we all get a chance to see a supernova in our galaxy in our lifetime, it's probably going to be Betelgeuse.
And what's that going to be? It's going to be light up the day?
We should be able to see it during the day. So, like, you'll have the sun up, and then if the sun is, far enough away from Betelgeuse in the sky, you'll see another bright dot in the sky. It'll look like a small star that's lit up in the sky. So it'll be incredibly bright. But it's plenty far away. Betelgeuse is like 640 light years away, ballpark. So that's really far. Like, it may not sound that far, but the galaxy's 100,000 light years across, and so it's close for stars, but still plenty far enough away that, it's not going to hurt us.
All right, so all the crap that comes out of it, it's going to be scattered before it would even reach this far?
Yeah. I mean, we can look up in the sky and we can see supernova remnants of past stars that have exploded in the galaxy, and they're all plenty far away. It doesn't bother us. We're not really going to get too much radiation or anything to worry about. We might get some cosmic rays that we'll be detecting, but nothing should really hurt us, which is good.
What about the asteroids we can't see?
Well, we probably have a higher chance of being destroyed by an asteroid than being destroyed by Betelgeuse exploding.
Well, and because we have a lot of evidence on Earth, too, and other planets that asteroids do hit and destroy us.
Well, and they hit us all the time. I mean, if you do the math, it's something like 30,000 tons of material strike planet Earth every year. Which is a lot. And I mean, we're not talking about like a 37,000 ton rock. It's, of course, tons and tons of tiny little bits of space dust. But a lot of stuff strikes planet Earth, and asteroids hit planet Earth. Every time you see a shooting star, that's just an asteroid coming by, or I should say a meteor coming by, crashing through the atmosphere. So it happens all the time, and the chance that we missed like a life-threatening one is pretty small, because NASA and other space agencies have telescopes that have been monitoring this, but you never know. I mean, things moving around in outer space all the time, and stuff gets kicked out of the way.
There's a lot of crap going on out there, right?
There is a lot of crap going on out there.
So, but it's full-time jobs for lots of people, I think, to watch our skies, right?
Oh, very much so. I mean, we've got space telescopes up there that have monitored the asteroids, and the cool thing is that we have enough mathematical knowledge to say, once we've seen an asteroid, we can track its motion. We just need to see it move a little bit, and we can figure out how it's going to orbit and if it's ever going to hit Earth. And you can go online. There are charts where NASA has predicted, like, when an asteroid is going to come by and what's its chance of striking Earth, how close it's going to be. So, and there's thousands and thousands of these potentially hazardous asteroids that we have charted, and we know when, where, and how to look out for them. So we're preparing ourselves as much as possible. Now, of course, I mean, things happen, right? Like in Russia a few years ago,
we missed that one,
came
right?
crashing down, and we did. So, and the explanation behind that is that they believe that it was an asteroid that was much closer to the asteroid belt that's between Mars and Jupiter, and it had a close encounter with another large rock. So, small rock, big rock. The small rock came by the big one, got tugged gravitationally, and it kind of sent it towards Earth on accident. So it was in a perfectly stable, normal, happy orbit out here, and then it just not collided necessarily, but got pushed, and that's why we didn't expect to see it until it was too late.
Okay. So, because that was terrifying.
It was terrifying, yeah, and I mean, It can happen, right? I mean...
Are you scared, though? You know a lot about what's going on. So you're not losing sleep over asteroids, are you?
I'm really not, you know what I mean? Things happen, and they could cause some damage, and right now this building could be struck by an asteroid. Like, who knows? But hopefully not, and there's a very good chance that it's not going to happen. So, I mean, of all the things to worry about in the universe, I wouldn't be terribly worried about an asteroid strike. But
what scares you most, then?
Oh, I had a feeling you were going to ask that.
Of course,
terrifying.
About it.
I think I'm more worried about solar flares, like the sun destroying us and hurting us, than I am an asteroid. And before we talk about the sun for a second, like, we should be prepared, right? Like, an asteroid could come by and we might be able to see it, and we would have, some notice, days, weeks, months, years, maybe. So we should probably come up with a contingency plan, like, what do we do if the asteroid is headed towards Earth? But I mean, the sun is also very violent. It sends out flares all the time. And if any of them are large enough and come in direct contact with Earth, fries our satellites, kills our power grids, destroys parts of the atmosphere, I mean, it's bad news for us. So there's a lot of things that can kill us in outer space. And
is that hard to know when?
Oh, yeah.
Like, solar flares just happen and we just observe?
I mean... So solar flares, the sun goes through cycles. It goes through active cycles where there's lots of flares and sunspots and other solar activity. And the sunspot cycle is 11 years. So every 11 years we see a peak, lots of sunspots and solar activity, and then a trough. So not as much. And right now we're headed towards a solar minimum. But just last week or 2 weeks ago, I think it was, we had a geomagnetic storm, part of a solar flare, come flying by and hit us. And it wasn't terribly damaging, but there's always a chance that we're going to get struck, that something is going to hit us and fry everything. So I'm a little bit more nervous about that than I am the asteroids, because
that thing's on fire, and they're all the time.
And we don't have any way of stopping it. Like,
no.
When the sun erupts, if a flare was headed directly towards Earth, and again, the chances are still small because the sun is far away and we are really tiny and things have to line up just right for it to happen. But we have about a day or two warning. Like, we can see the flare erupt.
No, Valerie, I don't want to hear a day or two.
That's it, because we can see it erupt. And the speed of light, we're 8 light minutes from the sun. So when something happens on the sun, it takes 8 minutes for us to know about it. But the physical particles, like the actual solar flare coming at us, takes about a day or two. It travels slower. So we've got about 2 days to get our shit together and figure this out. Whereas with an asteroid,
my palms are sweaty, by the way. Like, this...
I mean, an asteroid could happen tomorrow, but the chance that we'll know about it well in the future is much, much higher.
Okay, so we can prepare for an asteroid.
Prepare for that, yeah.
And solar flare, we just hope we get lucky.
Yeah.
We just hope our luck doesn't run out.
Exactly, and we have no way of predicting when and where the solar flares are going to happen. I mean, that's something that astronomers are working on. They're trying to figure out when solar activity is going to happen, predict where sunspots will be, when flares will erupt. By watching the sun, we should be able to use some triggers to know when things are going to happen, but we aren't that good at it yet. We can't really predict what's going to happen on the sun.
Oh my. Our sun is pretty awesome, right? It's just is it just like an average sun, right?
Yeah,
average size, average life.
It's really middle to small. So stars range anywhere from it goes 0.08 solar masses, so smaller than the sun, to about 150 solar masses. So we're kind of right in the middle. And it's just an average star, nothing terribly spectacular about it.
It's ours. It's spectacular.
It's our star, right?
It's spectacular.
It's keeping us warm. We on Earth are in the right spot to be the right temperature, have water, all that good stuff. But yeah, it's just an average, normal size.
But it might kill you.
But it might kill you. I mean, we can say that about a lot of things in space. You know?
Do you know much about gamma ray bursts? Because those were the recent thing that has terrified me.
I know a little bit about them. I know that they can come from supernovas and they can come from other stellar explosions in outer space. And, basically any time a large amount of high energy particles comes your way, you're in trouble. Whether it's in the form of gamma ray bursts or X-rays or the UV light that comes from the sun. I mean, that's why we put on sunscreen every day, right? Is because the sun emits these nasty high-energy particles our way, and thankfully we have an atmosphere that protects us from a lot of that, but it's obviously not 100%, so...
Are we gonna say if we keep chopping down our trees and keep throwing all this carbon dioxide in the air? Are we decreasing the effectiveness of the atmosphere to protect us from these sorts of things?
Yeah. So yes and no. The main thing that protects us from like the UV rays and stuff is our ozone, the O3. And any extra damaging stuff that we put there can destroy our ozone. And if we lose our ozone, we let through a lot more UV light, specifically the higher energy UV light that will burn us much faster and give us cancer much faster. So aside from the whole warming up the planet aspect, all of this harmful stuff that we put in the air, which isn't just carbon dioxide, all sorts of, other harmful things, are destroying different pieces of our atmosphere, and we have no way of getting it back. We can't just create a bunch of ozone in a lab and shove it up there and, hope that everything is happy again. There's holes in our ozone, and there are places that planes can't fly so high, and as the ozone in the atmosphere shifts, that hole moves, and there are places where it's more dangerous to be on Earth, and it's bad news. So we really need to protect our planet, and we don't have to get into the whole climate change thing, but just overall, from both a surviving with the climate and an astronomical danger standpoint, we really need to protect our planet because it's the only one we have, and it's done a pretty darn good job of recycling and keeping us safe. But if we start to destroy it, there's no turning back. And we're already starting to be on that route, unfortunately, of doing damage that's irreparable to this planet.
I love this planet so much.
I know, me too.
This planet's
so
great.
We don't have any other place to go. I mean, in all
and why would you want to?
sense,
People talk. Of course, Elon Musk, his crazy ass. They want to go to Mars, and I'm sure you, as an astrophysicist, want to go.
Of course, but
I don't want to leave ever. I love Earth. Earth is awesome.
Earth is really great, and Mars is gonna be awesome. It's gonna be awesome to go, and I really hope we get there. But there are so many hurdles that we have to jump over, and it's not just getting there. It's not just developing a space shuttle that's going to take us there safely and potentially get us back. But
that's the big problem, right?
Getting us back is twice as hard. But think about everything that Earth has that Mars doesn't. Planet Earth has air we can breathe. It's got water. It's got plants and animals and food that we can eat. It's got an atmosphere that protects us. It's got gravity that our bodies are familiar with. When we go to Mars, we have all these issues. There's the obvious ones. There's no food, no water, no air to breathe, right? And some of that we can deal with. We have equipment. We can make our own oxygen. We can bring our own food, whatever. But it's the other things that we don't yet know how to handle that are difficult. First thing is smaller planet, lower gravity. Our bodies are not used to being in a low gravity environment. And we see this with the astronauts on the space station. Their spines change. Being in that zero gravity, their digestive system changes. Everything internally in their body is not used to the fact that things aren't being pulled down anymore. Their body has to get used to that. So I think how our bodies function on Mars is going to be very different over long periods of time. And the other thing is all of this dangerous stuff we've talked about. We have an ozone. We have a magnetic field around Earth that protects us from solar wind. Mars doesn't have any of that. Mars has this incredibly thin carbon dioxide atmosphere that is pretty much useless. And, we might be able to take some of the oxygen out of it and use that to breathe, but it gives us no protection. So we would have to wear very protective spacesuits and be indoors as much as humanly possible to protect ourselves from these things that the Earth just gives us a natural protective layer for. And I think that's going to be the hardest part to overcome. We'll see humans get there. I have confidence in that. But surviving for long periods of time, that's going to be the problem because cancer is going to set in. Radiation burns are going to set in. If a solar flare heads their way, like I said, 2 days and you're dead. There's no second option there. So, that's the trouble,
It'll be an entirely different species of human, right? Say if there's a couple generations of people that grew up on Mars and they grew in the womb and that gravity and dealing with that.
It'll be a fascinating biological thing to understand, the first humans that are born on Mars, if that ever happens, because I would be fascinated to know how quickly the human body can adapt to such a different change, because like we said, different gravity, different radiation, and we know that our bodies and all of the life on Earth has changed over time, but it has changed over long periods, partly because the Earth has changed very slowly over long periods of time, but throwing a human being into such a sudden changed environment, I wonder if it'll take a long time or if our bodies will adapt like that. That'll be a fascinating thing to see.
That is fascinating to think, because when you look at nature and you see evolution happen, and it seems like how do certain animals in certain areas, just think of humans, people that live closer to the equator have darker skin, right? People that live north, we've genetically said, all right, we need lighter skin to absorb vitamin D better, right?
Exactly.
So it's like, how long does that really take?
Yeah.
Like, is Mars going to be a generation or two? Be like, oh, but like nature, is it that crazy?
Yeah.
Is it like a computer program, which is like, beep, 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 you're fine now, you can live on Mars?
Yeah.
There could be different people, and that's gonna happen, right?
I think so.
That's gonna happen. But number one is we gotta take care of Earth.
Exactly.
Oh God, that's so much easier.
Right.
That's so much. Let's do both
Earth
at the same time.
Yeah, exactly. There's no reason to choose one or the other, right? And I mean, that's always been the argument with all of these new energy sources. There's no reason that you can't do both at the same time. I'm not saying give up on coal and oil and all of that and just instantly switch to solar power and wind power. Let's do both at the same time and work towards becoming a better planet, It doesn't have to be a sudden change.
Are we going to survive?
I think we're fine. Of all the mind-blowing things we've talked about today, nobody should walk away scared or nervous. There's a lot of cool things happening in outer space, and there's a lot of smart people watching out for them. So I think we're going to be fine. And I think it's just going to be a wonderful adventure. We're going to look for the aliens. We're going to try and get to Mars. We're going to do all these cool things that, we're going to see in our lifetime.
This feels like it's the gold. I said that earlier, the golden era, or just the best, the Christopher Columbus exploring, and you're part of that. You're on that team.
Yeah,
you got to go into work and just read crap and just think about things and look at, applying for the crazy NASA alien job. Sure. Like you're at the forefront of the explorers. You're gonna learn new stuff.
Yeah.
Like there's nothing else out. Like there's so much more to learn. And
there is.
I think we need more and more generations of people like that. There's we don't know. There's still so many questions. Because you're going to die without knowing crap, right? Like you and I are going to die and be like, oh, never figured dark energy out. I hope the next people do.
Right, exactly.
So I think we just need more and more generations. That's what I hope this eclipse does. I was thinking about this the other day. I hope this eclipse going across the whole United States just inspires generations of people and kids. Kids are people, but kids to be like, I got to figure this out. This is fascinating.
Right.
And
you just need that one little trigger, to get your mind in the right direction, and then supportive parents, of course, and then just
your dad making you watch Star Trek and deliver newspapers.
Exactly, right?
All right. All right, Valerie, I think that's a great spot to end.
Sure.
My mind is sufficiently blown. I'm mildly scared, but mostly fascinated.
Good.
All right. Let's do this again in a few months.
Sure, that would be great.
Awesome.
Maybe after the eclipse, we'll do a little revisit of what actually happened and are people inspired to move forward.
I hope so. Because we're setting a couple things up in the eclipse to study the corona and crap, right? I think. Like there's
NASA's on it.
I think they're studying Mercury as well. We're going to be able to study the composition of Mercury for the first. I don't know. I read something about that recently. I'm probably making stuff up.
Yeah, it's all good.
Don't fact check me. I make things up all the time.
It's all good.
Thanks again, Valerie. This was awesome.
You're welcome.
Valerie Rapson, Dr. Astrophysicist.
Yes.
Awesome. Thank you.